Greetings, differential equations fans. Welcome to this video on first method for solving higher order differential equations. We're going to have a look today at constant coefficient differential equations. We'll start by having a look at sort of the overall goal, the equation we're going to be solving. We'll look at how to construct a solution. And we'll probably quit there, and in part 2 of this video we'll have a look at a few applications of these differential equations. So here's the goal. We're trying to solve the second order constant coefficient homogeneous differential equation ax double prime plus bx prime plus cx equals 0 with initial conditions given by the zeroth and first derivative at time 0. Again, here a few keywords, second order because it's a second order differential equation. Constant coefficient, meaning that the coefficients of the unknown function are constant. And again, homogeneous because the right-hand side is equal to 0. So in order to get a better grasp on these type of equations, we'll go ahead and define the linear differential operator as L. It's going to be Lx is defined to be ax double prime plus bx prime plus cx. And you can think of L as we go forward as just a specific way to mix up the unknown function and its derivatives. So you can think of it as a recipe, if you like, in this case with amount A of the second derivative, amount B of the first derivative, and amount C of the zeroth derivative or the unknown function itself. Now, this operator is linear because it has the properties that the image or applying this operator to a sum is the same as applying the operator to the first and the second. So L applied to x1 plus x2 is the same as Lx1 plus Lx2. And similarly, applying L to a constant alpha times x1 is the same as alpha applied to times L applied to x1. And we can see that with our differential operator defined to be Lx is ax double prime plus bx prime plus cx, we can rephrase our differential equation as a homogeneous differential equation, just call it Lx equals 0. So it may not be entirely obvious why that's convenient here, but as we go forward, we'll see that this notation is pretty useful for us. Okay, as an example of why it's useful, here's a first example called homogeneous superposition. So let's suppose that we've defined our differential operator L as previously, and let's suppose that x1 and x2 are both solutions of the homogeneous differential equation Lx equals 0. Then it turns out that any constant c1 times x1 plus any other constant c2 times x2 is also a solution. And to see this, we just substitute that function c1x1 plus c2x2 into the differential equation and use those properties of linearity that we saw just a moment ago. So the differential operator applied to c1x1 plus c2x2 is the same as the differential operator applied to the sum, right? So c1x1 plus the differential operator applied to c2x2. And then we know that constants can be pulled out front here, so this is the same as c1 times Lx1 plus c2 times Lx2. Now, of course, x1 and x2 are solutions themselves, so when you hit x1 with L, you get out 0, and when you hit x2 with L, you also get out 0. So we can see that c1x1 plus c2x2, when hit with L, gives you 0. It's a solution of the differential equation. Okay, this is a special combination of x1 and x2. Here's a little bit of terminology. The function c1x1 plus c2x2 is called a linear combination of x1 and x2. So those with linear algebra are familiar with that terminology. Another bit of terminology from linear algebra that we're familiar with is linear independence. So when x1 is not a scalar multiple of x2, the functions are linearly independent. And if x1 and x2 have two properties, namely that they are linearly independent solutions of a differential equation Lx equals 0, then the set x1, x2 is called a fundamental set of solutions. Okay, so a few expectations on this second order differential equation. We sort of expect to have to somehow integrate twice to integrate out these two derivatives. And in that sense, we expect two constants of integration. And in some sense, we expect a two-parameter family of solutions. From that two-parameter family of solutions, that's a general solution, we would expect to be able to select a family member that satisfies the given initial value problem. And it turns out that that initial value problem has a unique solution on the entire real line. Its interval of existence is minus infinity to infinity for this constant coefficient differential equation. Okay, so the general solution, as it turns out, of our homogeneous constant coefficient differential equation is just given by a linear combination of those two linearly independent solutions from a fundamental set of solutions. So that gives us a strategy for solving this homogeneous differential equation. This tells us that to solve a second order homogeneous differential equation that's linear of the form Lx equals 0, first we need two linearly independent solutions. We can identify a fundamental set of solutions as x1, x2, and then the general solution is just a linear combination of those two linearly independent solutions. And again, it's a general solution in the same sense that we had a general solution for first order equations, namely that we can always choose the constants C1 and C2 to satisfy any correct set of initial conditions given by x prime at 0 and x at 0. Okay, so here is a construction of our fundamental set of solutions in the case of this constant coefficient second order homogeneous differential equation. And in order to do that, we'll first have a look at the analogous first order problem. So the first order constant coefficient homogeneous differential equation is just given by ax prime plus bx equals 0. Now, we know full well how to solve this differential equation. The differential equation turns out to be separable, it turns out to be linear, and it turns out that we can also just recast it as an exponential growth or decay equation. So we can rewrite it as x prime equals lambda x, where lambda is equal to minus b over a. So of course we know the solution of that equation. The general solution is given by some constant times e to the lambda t. Okay, so with that in mind, we'll sort of try a similar function for our second order constant coefficient homogeneous differential equation Lx equals 0. So here we'll just try a solution of the form e to the lambda t. Okay, well, if we want to try this solution, we'll plug it into our differential equation. So in order to plug something into our differential equation, we'll need to identify the 0th, first, and second derivatives, and there they are, just with the derivative of this exponential function. And we can see then how to substitute into our differential equation. So Lx, again, is a parts of x double prime plus b parts of x prime plus c parts of x, which we can substitute those expressions for x prime, and x double prime, factor and rewrite it as Lx is equal to a polynomial in lambda all times e to the lambda t. Okay, so what do we want to pop out when we hit x with L? We're hoping that we pop out 0. In other words, x is a solution if this polynomial times e to the lambda t is equal to 0. Of course, e to the lambda t is never 0, so we can see that x is a solution if lambda is a root of this quadratic equation. Okay, so in some sense here we've done something really impressive. We've reduced the question of solving a differential equation to the question of solving an algebraic equation. Now, we know all about solving algebraic equations. If we want to solve an algebraic equation, we call this a characteristic equation. We can do that by just using the quadratic formula. Okay, so this trial solution e to the lambda t of the second order constant coefficient homogeneous differential equation gives rise to the characteristic equation, which in this case is a quadratic, a lambda squared plus b lambda plus c equals 0. So if lambda is a root of the characteristic equation, then e to the lambda t is a solution of Lx equals 0. Okay, so again, these lambdas are called eigenvalues, And we know from our study of algebra that eigenvalues or roots of this quadratic, they might be real repeated, they might be real distinct, or they might be a complex conjugate pair, just depending on the value of the discriminant, that is b squared minus 4ac. Okay, so it turns out that each case gives rise to two linearly independent solutions. And again, that's what we're looking for here. We're looking for two linearly independent solutions to this differential equation. Those two together form a fundamental set of solutions. And then the general solution is given by a linear combination of those linearly independent solutions. So we'll go ahead and look at each of these cases individually. So here's the first case. Let's suppose that the eigenvalues are real distinct. Okay, so if lambda 1 and lambda 2 are the eigenvalues, then two solutions are e to the lambda 1t and e to the lambda 2t. Of course, since lambda 1 and lambda 2 are different, a fundamental set of solutions is given by e to the lambda 1t and e to the lambda 2t, right? Those are two linearly independent solutions. And we'll come back to the general solution in just a second. In the case of a real repeated eigenvalue, one solution is e to the lambda t, and it turns out that another solution is t e to the lambda t. Okay, you can verify this just by plugging that solution into the differential equation. For the time being, just trust me that this is the second linearly independent solution, in this case of a real repeated eigenvalue, and we'll derive it a little bit later on. So again, certainly x1 is not a scalar multiple of x2. Those are linearly independent functions, both of which are solutions to the differential equation. So a fundamental set of solutions is given by e to the lambda t and t e to the lambda t. Okay, and in the third case, the case of a complex conjugate eigenvalue, we'll go ahead and just look at one complex valued solution here. I'm going to call that z of t. That's e to the alpha plus I beta t. Okay, we can use properties of exponentials to write that as e to the alpha t times e to the I beta t, and then we can use Euler's formula to express e to the I beta t as cosine beta t plus I sine beta t. Now I'm going to go ahead and call that first function e to the alpha t times cosine beta t x1 of t, and I'll call the second function e to the alpha t sine beta t as x2 of t, and if you note that that z satisfies the differential equation, that means when we plug it in, we had better pop out 0. So LZ is 0. Of course, since z is equal to x1 plus I x2, we can use linearity to see that Lx1 plus I times Lx2 is 0, which tells us actually that both x1 and x2 are solutions of the differential equation. Now this is really what we wanted. We wanted two real valued solutions that are linearly independent. Certainly those functions are not scalar multiples of each other, so they're linearly independent. So those two functions together, e to the alpha t cosine beta t and e to the alpha t sine beta t, form a fundamental set of solutions. Okay, so go ahead and summarize that and write down at the same time the general solution to the differential equation in the case of those different roots. So in the case of real distinct roots of the characteristic equation, the general solution is a linear combination of e to the lambda 1t and e to the lambda 2t, which is c1 e to the lambda 1t plus c2 e to the lambda 2t. In the second case, the case of a real repeated root, the fundamental set of solutions is given by e to the lambda t and t e to the lambda t, so that, again, the general solution is a linear combination of those linearly independent solutions, and it's common to factor out the factor of e to the lambda t to express the general solution as c1 plus c2t all times e to the lambda t. In the case of complex conjugate eigenvalues, similarly, the fundamental set of solutions is the exponential e to the alpha t times the cosine of beta t and e to the alpha t times sine of beta t. The general solution is a linear combination of those two linearly independent solutions, which once again we typically factor out the common factor, the exponential, to write this solution as c1 cosine beta t plus c2 sine beta t all times e to the alpha t. It's worth mentioning that in the case of purely imaginary roots, lambda equals plus or minus I beta, you can think of this as the complex conjugate case where alpha is equal to 0. Then the general solution is just a linear combination of cosines and sines, as you see here. Okay, so we've been able to derive the fundamental set of solutions in each of the cases where the eigenvalues are either real distinct, real repeated, or a complex conjugate pair, and we see how to write the general solution as a linear combination of those two functions forming the fundamental set of solutions in each case. I'll mention here also that there's a typo in Logan at this point. It turns out that they have a mistake for one of the forms for the general solution, so just double check that and refer to these few slides for the general solution. Okay, so a few examples that illustrate finding the general solution to a constant coefficient, second order constant coefficient homogeneous differential equation. Okay, so here's the first one. We want to solve x double prime plus 6x prime plus 8x equal to 0. We'll start off just like we did in the general case by trying a solution of the form x of t equals e to the lambda t. So play the same game, identify what it means to plug that function into the differential equation in this case, and we can see that x of t plugged in gives you out, again, a quadratic lambda squared plus 6 lambda plus 8 all times the exponential e to the lambda t. Now, of course, this is a homogeneous differential equation, so we would like to be able to plug this function in and pop out 0. So e to the lambda t is the solution, again, if the quadratic times e to the lambda t is equal to 0, or, since e to the lambda t is never 0, if lambda squared plus 6 lambda plus 8 is equal to 0. Okay, so that quadratic forms the characteristic equation in the case of this differential equation. And you can sort of see where those coefficients come from, right? The coefficient of 1 from the second derivative, the coefficient of 6 from the first derivative, and the coefficient of 8 from the 0th derivative. So this problem is cooked up so that the quadratic factors quickly, and we can see that the eigenvalues in this case are -2 and -4, real distinct eigenvalues, so that a fundamental set of solutions is given by e to the -2t and e to the -4t. The general solution in this case is a linear combination of those two linearly independent solutions, c1 e to the -2t plus c2 e to the -4t. Again, as expected, a two-parameter family of solutions. Okay, second example here, solving a differential equation. Here we'll go ahead and have a look at solving x double prime plus 4x prime plus 4x equals 0. So again, we'll try a solution of the form e to the lambda t, and in this case we're going to go ahead and jump straight to the characteristic equation. E to the lambda t is a solution of the homogeneous differential equation if lambda is a root of this quadratic, lambda squared plus 4 lambda plus 4 equals 0. This polynomial 2 factors nicely as lambda plus 2 quantity squared, which indicates those real repeated roots. The real repeated eigenvalue is lambda equals -2, so that a fundamental set of solutions is given by e to the -2t and t times e to the -2t. Again, the general solution is a linear combination of those two linearly independent solutions, which we've written here in factored form as c1 plus c2t all times e to the -2t. Again, that's the expected two-parameter family of solutions. And again, it's the general solution in the sense that we could use that form to correctly satisfy any given initial value problem. Okay, so we don't have an initial value problem here, we just have a differential equation, but you could use that two-parameter family of solutions to select the correct family member in order to solve an initial value problem. Okay, a third example here is a differential equation x double prime plus 2x prime plus 2x equals 0, a homogeneous second order constant coefficient differential equation. Again, we'll try a solution of the form e to the lambda t and jump straight to the characteristic equation e to the lambda t is the solution of Lx equals 0 if lambda is a root of the characteristic equation lambda squared plus 2 lambda plus 2 equals 0. Okay, in this case I've used a age-old method from pre-calculus called completing the square to simplify this equation, writing it as lambda plus 1 quantity squared all plus 1, which tells us that the complex conjugate eigenvalues are lambda equals minus 1 plus or minus I. So again, we'll pick off the alpha as minus 1 and the beta as 1 here to see that a fundamental set of solutions is e to the minus t times cosine of t and e to the minus t times sine of t. General solution, again, a linear combination of those linearly independent solutions, which again we've written here in factored form as c1 plus c1 cosine t plus c2 sine t all times e to the minus t. Okay, one more example before we move on. Go ahead and have a look at a fundamental set of solutions for the differential equation 4x double prime plus 9x equals 0. Okay, same strategy as before. Try a solution of the form e to the lambda t and see that e to the lambda t is the solution of the homogeneous differential equation if lambda is a root of this characteristic equation 4 lambda squared plus 9 equals 0. Of course, you can see here that that tells us lambda squared has to be 9/4, giving rise to the purely imaginary eigenvalues plus or minus 3/2 I. Okay, so again, a fundamental set of solutions in this case is cosine of 3/2 t, sine of 3/2 t, and the general solution, a linear combination of those two linearly independent solutions, c1 cosine 3/2 t plus c2 sine 3/2 t. One more example before we move on with some general comments about construction of solutions. So here's an initial value problem, a second order constant coefficient homogeneous initial value problem for which we've seen the general solution a moment ago as c1 cosine t plus c2 sine t all times e to the minus t. Okay, so in order to satisfy the initial conditions, we'll just have to choose our family member correctly. You can see that x prime of t using the product rule can be expressed as some sines and cosines times an exponential, so that the initial condition x of 0 equals 1 gives us one relationship between c1 and c2, and the second initial condition x prime of 0 equals 3 gives us a second relationship between c1 and c2. Now, of course, cosine of 0 is 1 and sine of 0 is 0, simplifying the system quite a bit. Here is the resulting system of equations for c1 and c2. It's c1 equals 1 and minus c1 plus c2 equals 3, so that c2, you can see quickly, has got to be 4. Now, it turns out that that requirement that our solutions be linearly independent in this general form guarantees that we can always solve this system of equations that we get for c1 and c2. And that's kind of a cool linear algebra result that's beyond the scope of what we want to do here. In any case, go ahead and convince yourself that the solution is c1 equals 1 and c2 equals 4, so that the solution to the initial value problem in this case is given by cosine t plus 4 sine t all times e to the minus t. Okay, talk a little bit about a special differential equation that ends up popping up quite a bit, the hyperbolic form. So the differential equation x double prime minus a x equals 0 has a fundamental set of solutions e to the at and e to the minus at. And of course you can see this just as we did a moment ago, seeing that the eigenvalues of the characteristic equation lambda squared minus 1 equal to 0 is given by plus or minus alpha, real distinct eigenvalues, so that the general solution is a linear combination of those two exponential functions. Now, it turns out to be convenient to express the general solution of this differential equation in a slightly different way in terms of hyperbolic, cosine, and sine. These are functions that you probably saw in Calculus 2. Hyperbolic cosine, pronounced cosh, of at is e to the at plus e to the minus at over 2. And similarly, hyperbolic sine, or sinh, of at is e to the at minus e to the minus at over 2. Now, cosh and sinh have the property that their derivatives are related, namely the derivative of cosh AT is given by A sinh of AT, and similarly, the derivative of sinh AT is given by A cosh AT. And you can go ahead and convince yourself just by having a look at the derivative of sinh and cosh in terms of those linear combinations of the exponential functions. That being said, we can see quickly that when x1 is cosh of AT and x2 is sinh of AT, that cosh and sinh both have the property that they satisfy this differential equation x double prime minus a squared x equals 0. Okay, those are two functions which are not linearly dependent, right? They're linearly independent. So they together form an alternate fundamental set of solutions to the differential equation x double prime minus a squared x equals 0. So that the general solution to that differential equation can be expressed as b1 times cosh of AT plus b2 times sinh of AT. I'll point out that cosh of 0 is 1 and sinh of 0 is 0, so it turns out that solving initial value problems when you express the solution of this particular differential equation in terms of sinh and coshes is a little bit easier than it is expressing the solution in terms of exponentials instead. Okay, we'll go ahead and stop here. That was a pretty long video, but went over the construction of the solution of this homogeneous second order constant coefficient differential equation. And again, it all depends on the roots or of the corresponding characteristic equation, which we refer to as eigenvalues of the differential equation. In our next video, we'll go ahead and have a look at a few applications of these type of differential equations in the context of our two model systems, the mass spring system as well as the RLC circuit. Okay, thanks for watching, and so long for now.